In this video, we take up a particular kind of motion problem, rectilinear motion problem, and that's the one in which the acceleration is a constant. This is an important situation because the Earth's gravity is it provides a constant acceleration to things that are falling. And so let's suppose that a of t, the acceleration function, a of t, is the number a, whatever that is. In case of Earth, it's negative 32 feet per second squared. All right, and that v at time 0 is v sub 0, and also s at time 0 again is s sub 0. What we want to do is find the velocity and the position functions. So let's first of all look at the velocity function. Well, the velocity function is an antiderivative of the acceleration function. Now remember, this acceleration function is a constant. It's just a number. So I could take that out of the integral, and I just have one dt left. Now I have to think, who has 1 as its derivative? Well, of course, with respect to t, that would be t. So this will be a t, then plus some constant. I'll call this c1 because we'll have a second constant in just a few minutes. And so now we have our acceleration function. Well, we know it almost, except we don't know what c1 is. So that's what this initial condition is for. Okay, so we know that v evaluated at 0 is v aught. All right, that's given to us. And v evaluated at 0 is v of t, where each instance of t has been replaced by 0. So that would be a times 0 plus c1. And of course, that means skipping the one in the middle here. That means that v aught is equal to c1. So here's my velocity function completely known. It would be at plus c1, which was v0. So there's my velocity function. So if I have a constant acceleration, and I know that as a, and if I know the initial velocity, the velocity at time 0, this would be my velocity function. All right, now let's go on to find the position function. To find the position function, well, the position is the antiderivative of velocity, which we just found to be at plus v0. And of course, let's see if we anti-differentiate this. Remember, a is just a number in the case of gravity, negative 32 feet per second squared. V is just a number. If it starts from rest, v sub 0 would be 0. So this is going to be, all right, when I integrate t, I get t squared over 2. So this is going to be a t squared divided by 2 plus v is just a number. So when I integrate it, I'll get v aught times t, plus then I'll get another constant of integration, which I'll call c2, so we don't confuse it with the constant we got in the previous integration. And now we know s of t except for the c2, but that's what this initial condition is for. Okay, so s of 0 we know to be s0. And s of 0 is just s of t, where each instance of t has been replaced by 0. So it's going to be a times 0 squared over 2 plus v aught times 0 plus c2. Well, this means that s0 is equal to c2. And so now we know we can replace the c2 with s0, and we'll know the position function precisely. S of t is a t squared over 2 plus v naught t plus s naught. That's our acceleration function, and our velocity function from before was a t plus v0. So if we have a constant acceleration of a, all right, initial velocity of v0 and initial position of s0, our velocity function is at plus v0, and our position function is at squared over 2 plus v0t plus s0.